So here is a section from Chapter 19, Electrochemistry. This chapter will be covered in 1B, if you take that class. But we need to cover a method of balancing redox reactions called the half reaction method. So let's take a couple of minutes to review balancing redox reactions. We just covered this in Chapter 4, but it bears repeating. So we learned this mnemonic, oil rig. Oxidation is loss of electrons, reduction is gain of electrons. We also learned about oxidation states, which is a made-up way of keeping track of shifting electron density. So oxidation is an increase in the oxidation state. That if you're actually losing electrons, that's an increase in charge. So it's just a different way of stating the same thing. Reduction is a decrease or a reduction in the oxidation state. The oxidation state will go down, become more negative if you're gaining electrons, right? Reduction is gain of electrons. Reduction is a decrease in the oxidation state. So they're stated differently, but they both mean the same thing. So we can look at an equation like this: calcium reacting with water to form calcium hydroxide and hydrogen gas. And we can look at the oxidation states for calcium here being an element, no charge on these atoms, the oxidation state is 0. In water, we have to use our rule, our list of priority Fe765, FHO765. So hydrogen gets its first choice. When it gets to choose what oxidation state it gets, it's going to choose the same as it would have as an ion. So it's going to choose +1. Oxygen then has to make up the difference. The sum of these oxidation states for this neutral molecule have to add up to 0. So oxygen is -2. Over here we have calcium and hydroxide. The calcium ion has a +2 charge, and so it has a +2 oxidation state. The hydroxide ion is OH-. So we see that its oxidation numbers for oxygen and hydrogen have to add up to -1. Again, Fe765 goes hydrogen first and then oxygen. So hydrogen gets what it wants and oxygen has to make up the difference. And then for hydrogen, that's a neutral element, and so we have a 0 oxidation state there. So when we balance a redox reaction, we have to have the mass and the charge balance. Here from the oxidation states, we see that calcium has gone from an oxidation state of 0 to an oxidation state of +2. That's an increase in the oxidation state that's being oxidized. Hydrogen has gone from +1 to 0. That's a reduction in the oxidation state. That's a reduction. You can also think of it in terms of gain and loss of electrons. Calcium has lost 2 electrons to go to a +2 ion. Hydrogen is not as obvious here because it was in a molecular compound here, and so it's harder to think of it gaining or losing electrons. But it has gained electron density. So when we balance this, the mass and the charge must balance. And so sometimes for a redox reaction, you can balance it the way we have by inspection and have all the atoms and stuff correct, but you'll end up with a charge imbalance. And so that's where we need the half reaction method, where we're going to take this equation, we're going to separate it into 2 half reactions, one for the oxidation, one for the reduction. We'll balance those separately and add them back together. Okay? This is a review of oxidation states. Basically, this comes down to oxidation states act much like ionic charges, even though they are not ionic charges. Just like with ionic charges, if the molecule is neutral, then the charges add up to 0, the oxidation states add up to 0. If you have a polyatomic ion, they add up to the charge. For metals, generally, the oxidation state is the same as the ionic charge. And this is the one part that's different, and we remembered this by thinking about Vietnamese noodle soup, Fe765. FHO 765, and it's an order of priority. So that's assigning oxidation states. We talked about that in chapter 4. So here's the procedure for the half reaction method. And this is for balancing aqueous redox equations. So they're in water, happening in water. And we'll start out by balancing in an acidic solution. So first thing is assigning oxidation states, identifying what's being oxidized, what's being reduced. This is needed so you can tell what's being oxidized to put in one half reaction and what's being reduced to put in the other. So you're going to separate the overall reaction and have one for oxidation, one for reduction. Then you're going to balance each half reaction separately. First, you're going to balance with respect to mass, the number of atoms of each kind of element. This is what we've been doing when we balance equations. Well, we're first going to balance all the elements beside hydrogen and oxygen. We're going to leave those for the last. When we need to balance oxygen, hello, Doceri, come back to me. I don't know, the pointer's dead. Balance the oxygen by adding H2O on whichever side is needed. That's going to mess up hydrogen, maybe introduce hydrogen into the equation, and we're going to balance the hydrogen by adding hydrogen ions. Come on. Okay, so then after we've balanced for mass, then we balance with respect to charge. So you look at the ionic charges on each side of the arrow, and they need to add up to the same number on each side. They're not necessarily going to be 0 on each side, but they need to be balanced. So we balance that by adding electrons. Okay, because oxidation and reduction involve the transfer of electrons. Electrons are being transferred. So after we get that all balanced, then we look at our two half reactions, and we need to make the number of electrons that are shown in those half reactions the same number. And so we may need to multiply one or both of the half reactions to get them into the same number. And that'll hopefully become more clear when we do some examples. Then we add the half reactions together. We cancel out the electrons and any other species that end up being the same on both sides, and then we double check, verify. So let's do some examples. We'll start out with some that are a little simpler. So balancing this redox reaction, here we have aluminum plus a copper 2 ion makes aluminum ion plus copper metal. If we look at this and just balance it by inspection, there's one aluminum on each side and there's one copper on each side. And so we think, well, what's wrong with that? It's balanced. The charge isn't balanced, though. On the left side, we have a total of a positive 2 charge. On the right, we have positive 3 charge. That's not balanced. Somewhere an electron just disappeared? That can't happen. So we're going to pull this apart. Let's just look at the oxidation states. That's not always absolutely necessary, but it's good practice. What's the oxidation state on aluminum? 0. And on copper 2 plus? Plus 2. How about aluminum 3 plus? Plus 3. And copper? 0. So we see here that the aluminum is going up in oxidation state, it's being oxidized, and the copper is going down, it's being reduced. So we're going to write one reaction, half reaction for oxidation and one for reduction. Doesn't matter which one you put first. I usually just start with this first species. So here's aluminum. And then I'm on the reactant side, I'm going to find the thing that goes with that. Aluminum can't turn into copper, so the other side must be that aluminum ion. Because aluminum atoms could turn into aluminum ions, right? So those two go together. And then I've got the copper 2 plus. I'm going to put that in my other half reaction. And that's going to form solid copper metal. 2 half reactions. First then, see I've got these are like our crib notes over here. separated into two half reactions, balanced with respect to mass. They're already balanced with respect to mass. So we're done with that one. Balance with respect to charge. So on the left side, I have 0 charge. On the right side, I have positive 3 charge. I need them to be the same, and I'm going to fix it by adding negatively charged electrons. So where do I need to put them? On the, well, if I put them on the left, if I put negatives over here, then this is going to be negative, and that's still going to be 3 positive. So I need to put them over here. If I add 3 electrons over there, 3 negative 1 charges and this positive 3 charge will add up to 0, which is what I have on the other side. You see that? Down here, I've got +2 and 0. All I can do is add electrons. And so I need to add electrons to the side that's more positive to bring it down. Okay? Now, we looked earlier and we said that the aluminum was being oxidized, right? Oxidation is loss of electrons. The aluminum is losing electrons. It's giving off electrons. The copper 2+ is being reduced. Reduction is gain of electrons. The copper 2+ is gaining electrons. So those work out. So now it's balanced. Yes?
So when you're adding electrons, why is it that you have to add it to the side where it's Al3+ and it's not okay if you add it to the aluminum?
That's a good question. So if I add, let's just take this away and add it to the other side. So if I add 3 electrons over here, now what's the total charge on this side? -3. And the total charge on this side? +3. They both involve a 3, but one's positive, one's negative. They're not the same.
Oh, it's not like a...
It's not like an opposite thing.
Yeah.
It's not an opposite thing putting ions together. We need the exact same number and the same sign. So that's why we need them on that side. And I'm sure other people had the same question. Okay, so there's our half reactions. Now what we need to do is we need to get the numbers of electrons released by the aluminum and the number of electrons gained by the copper to be the same number of electrons. That's what's going to fix the charge imbalance in our original equation. So we're looking for the least common multiple of 3 and 2. 6. If I multiply this by 2, I'll get 6 electrons. If I multiply this by 3, I'll get 6 electrons. Then I've got 6 electrons being released, 6 electrons being gained. They just go directly from one to the other, and they don't have to show up in the equation anymore. So what I'm going to do, because I sometimes forget what I'm multiplying by, I'm going to multiply this equation by 2 and this one by 3. You have to multiply everything, all the coefficients, in order to keep it balanced. So I'm going to have 2 aluminums, making 2 aluminum ions, and that's going to release 6 electrons. Still balanced, I'm just scaling up. Here I'm going to multiply by 3, so that's going to give me 6 electrons here, 3 copper ions, and 3 copper atoms. Okay?
So we're multiplying to the electrons.
We're multiplying everything in the half reaction so that we can get the number of electrons to be the same. Don't care about anything else. I want the number of electrons released in this to equal the number of electrons gained there. Okay? So then we're going to add these 2 equations back together, and we see that these 6 electrons cancel out. So this is like if you had 3x plus y equals z plus 3x. Could you get rid of the 3x on each side? Yeah. There's a 3x on each side. If you subtract 3x from each side, they go away. So you just cross them off and y equals z. That's all I'm doing. It just looks funky because there's all these letters. So that's what I'm doing with the electrons. you're always going to end up canceling out the electrons. There should never be any electrons showing in your overall reaction. So then I'm just going to write down everything else. And the order, as long as it's on the correct side of the arrow, the order doesn't actually matter. I like usually to follow the same order as in the original equation. So 2 aluminums and 3 copper 2 plus ions will form 2 aluminum ions and 3 copper atoms. And then you should double check and make sure that the charges on each side are equal. So here I've got a total of 3 times 2, a positive 6 charge, because this is 0. And over here 2 times 3, positive 6 charge and 0. So the charge doesn't change from reactants to products. It's the same, the overall charge. Electrons have moved from one substance to another, but we haven't created or destroyed electrons, because that's not possible. Yes?
You're not multiplying it 3 and 2 onto the electron, you're multiplying it to like the element.
Well, when I multiply by 2, I take all the coefficients in this balanced half reaction. So this was an understood 1, I'm multiplying by 2. This was a 1, I'm multiplying by 2. I started out with 3, and I multiplied by 2 to get 6. And down here, I had to multiply by 3 so that this number of electrons would be 6. And then these just happened to be 3 each. Okay. Any other questions? So this is a very simple one. We'll do some that are a little more complicated. So let's balance this one. Here we've got hydrogen ion plus chromium metal, giving us hydrogen gas and chromium ions. So again, we'll look at the oxidation states. What's the oxidation state of H+? Plus 1. How about Cr? 0. How about H2? 0. Each atom in that hydrogen molecule is 0. And Cr2 plus? Plus 2. So we've got the hydrogen being reduced and the chromium being oxidized. Oh, I didn't leave myself enough space. So H plus is going to go to H2 gas, because those are the things that have hydrogen. And then the chromium going to a different kind of chromium is the other half reaction. So that's separating into 2 half reactions. Okay? Balance with respect to mass. Well, is the top one balanced with respect to mass? No. I've got H2 over here, and I only have one H here. So I'm going to balance that by putting a 2 in front of the H plus. Okay? So I got 2 H pluses, and that'll give me the 2 hydrogen atoms that can make this molecule. Down here, I've got 1 chromium and 1 chromium. That one's already balanced with respect to mass. Then we balance with respect to charge. Is this balanced with respect to charge? Same number of charges on each side? No. I need to add electrons. Am I going to add them to the left or to the right? To the left, because this has the higher charge. This is plus 2, and this side is 0. Adding electrons brings the charge down, right? So I can't add it to this side, because that's going to make it even lower, and that's going to make things worse. So I'm going to add 2 electrons here. That's 2 negative charges, and 2 positive charges add up to 0, and then I have a 0 on the other side. Yeah?
So the hydrogen when it first started was the plus 1, but since we put in front of it now, it's plus 2, because we did count for each of them.
Yeah, so we have total of plus 2 charge because we have 2 hydrogen ions, and they're each plus 1. Yeah. So here I've got chromium with a 0 charge and chromium with a positive 2 charge. So again, this side is higher in charge, so that's the side I'm going to add the electrons to. And to get 2 plus down to 0, I need to add 2 negative electrons. The coefficient in front, the big number in front, just says how many of these things I have. Subscripts, charges refer to that individual piece, whether it's an atom, an ion, or a molecule. Okay, so are my number of electrons equal? Yeah, they are. 2 on each side, so I don't need to multiply this stuff. I can just add these things together. So 2 electrons on the left, 2 electrons on the right, those cancel out. And then I'm just going to copy down the other stuff. So I've got 2 hydrogen ions, those are aqueous, plus chromium. That's going to make a chromium ion plus hydrogen gas. Check the charges, check the mass balance, it should be fine. Any questions? Because if there's something that confuses you here, please ask me, because it's not going to get simpler. We're going to add in a little more complexity. Yes?
Why didn't you multiply this?
Why didn't I multiply? Because I already had 2 electrons on this side and 2 electrons on that side.
Okay.
So the idea of multiplying each is to get the same number of electrons so that you can cancel them out.
And the H2 went second in this one? Why didn't
Yeah, I wrote the H2 second here because I basically had a brain fart. I was zoomed in and I couldn't see that. Yeah. But it's like adding. 2 plus 3 is 5, and 3 plus 2 is 5. So in a chemical equation, we're adding things, and if you reverse the order, it's still okay. You just have to pay attention to the arrow and get things on the right side of the arrow. Okay? Okay, let's do this one. Crib notes are gone, and we've got an extra element in here. So the first step is putting in the oxidation states, and that's a good idea. It's not actually always necessary. A lot of these are going to have 2 reactants and 2 products, and you can clearly identify that Fe2 plus and Fe3 plus are going to have to go together, right? And then this guy and the other guy are going to have to go together. So you don't strictly have to do that. So I'm going to put Fe2 plus going to Fe3 plus as 1/2 reaction, and MnO4. Remember the name of that ion? Permanganate. Going to Mn2 plus aqueous. If you save a little space here for a coefficient, that makes it a lot neater and less erasing and recopying and stuff that has to happen. Okay, so what's the next step? Balance with respect to mass. So the first one, 1 iron and 1 iron. That's fine. Down here, 1 manganese, 1 manganese. That's all good. Oxygen. There's 4 oxygens on this side. There's no oxygen on that side. What the heck? How do you balance that? You add water molecules. And that's not just like making stuff up, because this is happening in an aqueous solution. There's a 1.5 gazillion water molecules around. They just weren't showing in that reaction, in the equation. So I'm going to add H2O. Water is a liquid at room temperature. I've got 4 oxygens over here, so how many water molecules do I need? 4. So great, we balanced the oxygen, but now we've put hydrogen in there that wasn't there before. We're going to balance that. We're going to balance the hydrogens by adding H+. So over here I have 8 hydrogen atoms. So then over here I need to put in 8 hydrogen ions. because that's what the directions tell us to do.
So those are the two big rules being, if you're adding hydrogen, you add hydrogen ion, and then if you're adding oxygen, you add H2O.
So when you're balancing for mass, you first make sure everything that's not hydrogen or oxygen is balanced. Then you balance oxygen, and if you need to add something in there, you add H2O. Then you balance hydrogen by adding H pluses.
Okay. And those are the only two rules with
For mass, yeah.
mass.
Those are the only two rules. Okay, so we've got mass balance. Now we need to balance charges. We do this by adding electrons. Fe2 plus goes to Fe3 plus. How many electrons do I need? 1. It's the difference in the charges. What side does it go on? It goes on the right. If I add 1 electron here, then this 1 negative charge and 3 positive charges gives me +2 on this side and +2 on that side. It doesn't matter what the total charge is, it just needs to be the same on each side. Down here, this is getting a little messier, right? Because we've got 8 positives here and 1 negative. So that's a total of what? 7. So on that side, we've got +7. And on this side, we've got nothing here and +2. Balancing with respect to charge, we are looking at ionic charges only. We're not looking at oxidation states. We're looking at actual ionic charges. So this side is more positive. How many negative electrons do I have to add to get 7 down to 2? 5. So I need to add 5 electrons. So any questions? The math here is not hard. It's adding and subtracting integers, but there's negatives involved, and so you sometimes have to stop and think about it longer than you think you should have to, but anyway, there it is. What's the next thing we need to do? We need to multiply to get the electrons the same on both sides. So in the first half reaction, I have 1 electron. In the second half reaction, I have 5 electrons. Those aren't going to cancel out. So 5, I could change this 1 into a 5 if I multiply this whole equation by 5. And then I don't actually have to do anything to the bottom one. So I'm going to multiply all the coefficients here by 5. It's still balanced because I'm doing the same thing to everybody. Now I have 5 electrons here, 5 electrons there, and so those are going to cancel out. The electrons are being transferred, but they kind of go behind the scenes. You don't actually see them moving in the balanced chemical equation. So now we add these together. So draw a line. And I'm going to try to do the same order. It doesn't really matter, but you got to have some guidelines in life. So Fe2 plus, there's 5 of those. And then I'm going to add in the the permanganate. 1 permanganate ion. And then I've got the 8 hydrogen ions. Again, the order is not important. And then I've got 5 iron 3 ions. And 1 manganese 2 ion. And 4 water molecules. And if you go through and check that, it's balanced with respect to mass and charge. Questions? If you do several of these, you start to remember what to do, and it's really not that bad. But you got to practice it a bit. It's a little bit like making a path in the grass. When I attended Iowa State University, and there was a big green, a quadrangle. It had sidewalks around the edges, but they waited a couple of years before they put any sidewalks through the middle. Because the students, of course, would cut across the grass, right? You get enough students cutting across the grass, they kill the grass in that area and make a path. We call that a cow path, because cows do that too. So they waited until the cow paths formed, and then they put sidewalks where the cow paths were. Then the students aren't killing the grass anymore, because they put the sidewalk where the students were going to walk anyway. Brilliant, right? How is a cow path made? One student walking through the grass is not going to make a cow path, right? It takes students doing it over and over and over and over again. To remember things like this, you need to make a cow path in your brain. And the way you do that is by doing it over and over and over again. If you make the cow path and then you don't keep walking on it and you wait long enough, the grass will come back. So you have to keep going over this stuff, so that when you get to the final exam, you still remember it. Okay? Let's do another one. Balance this reaction. Copper plus nitrate ion making copper 2+ and nitrogen dioxide. So we need to separate these into two half reactions. So we need copper on one side and the copper ion on the other side. And then we're going to put nitrate and NO2 together. Basically what you're doing is you're picking the two substances that are most alike, right? Because if you put copper on the left and NO2 on the right of one half reaction, you're never going to be able to get that to balance. So there's my two half reactions. Balance with respect to mass. So the first one is already mass balanced, 1 copper on each side. This one, we have 1 nitrogen on each side, 3 oxygens here, 2 oxygens there. What do we add to balance oxygen? Water. So I've got 3 oxygens and 2 oxygens. I need an extra oxygen on this product side, and so I'm going to add a water molecule. 3 oxygens on each side. Now I have to balance the hydrogens by adding hydrogen ions. So I threw 2 hydrogens into here, so I'm going to balance that by putting 2 hydrogen ions on the other side. It's hydrogen ions because that's the method. That's the only reason. Okay, so we've got mass balance. Now we need to charge balance. First half reaction, total of 0 on the left side plus 2 on the right side. We're going to add electrons so that we can get them to be the same. So if I add 2 electrons over here, I've got positive 2 and negative 2. That adds up to 0. And over here, I've got 0. Down here, on the right side, I've got overall 0 charge. On the left side, I've got 2 positive charges and 1 negative charge. That's a total of +1. To get that to be 0, like the other side of the half reaction, I need to add 1 electron. Now, do I have to put the 1 there? No, not necessarily. I need to fix these equations so that I have the same number of electrons showing in each half reaction. The top one has 2 electrons, the bottom one only has 1 electron. So I need to multiply everything in the second half reaction by 2. So I'm going to have 2 electrons, and if I multiply this 2 by 2, I'm going to get 4 hydrogens, 2 nitrate ions, 2 NO2 molecules, and 2 water molecules. It's still balanced for mass and charge. I have 2 electrons on each side. Those cancel out. And then I'm going to add these together. So I've got solid copper, and I have 2 nitrate ions. And I've got 4 hydrogen ions. And on the right side, I have one copper 2 ion. And I have 2 NO2 molecules and 2 water molecules. Any questions? Yes?
So when you're adding electrons, why did you add one electron to the bottom?
To this one? So if you just look at the green, here I have a total of +2 charge, and here I had a total of -1 charge.
Oh, okay.
Okay? Okay?
So the only thing that's going to trip us up when going through it is that there might be like an extra oxygen on one side or an extra hydrogen on one side, and that's really, it's not going to be like a whole other element.
We're not going to throw any extra elements in there. It's just going to be hydrogen and oxygen. And the reason that works out is because it's in water. Yeah. Any other questions about this one? I'm doing a lot of practice examples because you need a lot of practice examples. And I would encourage you to go home, catch the YouTube video, stop it where it's just showing the problem, and try to do it yourself. And then if you get stuck, you can advance the video and listen to the explanation and see it. And then, oh, okay, I know what to do now, and keep going. And go through those until you're like, okay, I think I've got the idea for this. Well, all of that's been in acidic solution. What if you have a basic solution? There's just one extra step here. And it happens in the balancing with respect to mass. We balance all the elements other than hydrogen and oxygen. We balance the oxygen by adding water. We balance the hydrogens by adding hydrogen ions. But to make it basic, we need to neutralize those hydrogen ions, because hydrogen ions are present in an acidic solution. So we're going to add hydroxide ions to neutralize the hydrogen ions. So if you have 3 hydrogen ions on one side, then you're going to add 3 hydroxide ions to both sides of that equation. That's not going to mess up the balancing. It's just going to change it from acidic to basic. Let's do an example. Balance this one in basic solution. So starts out the same. Separate into 2 half reactions. So we have I minus, aqueous on that side, and I2, aqueous on this side. And then the other thing in here is permanganate ion. And MnO2. Yes?
So we're only going to know how to balance it in basic or acidic if it tells us to do so.
Right. It will tell you in acidic solution or in basic solution. If you happen to come across one that doesn't tell you, isn't specific, acidic is easier, so do it in acidic solution. If whoever wrote the problem really cares, they should tell you. Okay, so balance with respect to mass. Here I have 1 iodine, and here I have 2. So I need to put a 2 in front of the I minus. Down here, I've got MnO4, MnO2. There's 1 manganese on each side, but here I've got 4 oxygens, and here I have 2 oxygens. I'm going to add water molecules to get those extra oxygens. So 2 water molecules. Now I have a total of 4 oxygens on this side and 4 oxygens on that side. Then I have to balance the hydrogens. So I have 4 hydrogens over here. So I'm going to add 4 hydrogen ions over here. So now I have my mass balance. Yes?
4.
Yeah, it's 4. And I said 4, didn't I? But I wrote 2. There is some sort of a glitch in my head. 4, thank you. I would like to pretend that I do that just to see if you're paying attention. But that's not the case. I screw up. Okay. This is where we have to add that one extra step. So this is basic solution. We can't have hydrogen ions floating around. So if we remember from talking about acid-base reactions, a hydrogen ion plus a hydroxide ion will combine to make a water molecule. So what we're going to do is we're going to add hydroxide ions to both sides. We have 4 hydrogen ions. We're going to add 4 hydroxide ions. So I'm going to add 4 hydroxide ions up here. And I'm going to add 4 hydroxide ions down here, over here. Four hydroxides and 4 hydrogens. Hydrogen ions. We can simplify that, right? Because each hydroxide and hydrogen ion will combine to form a water molecule. So if I have 4 hydroxides and 4 hydrogen ions, how many water molecules would that make? 4. So I'm going to erase that and rewrite that. That's 4H2O.
So that's only hydrogen ions.
Only hydrogen ions will do that, not hydrogen molecules or anything else.
Okay.
Just H+.
Okay.
Because of this net ionic equation. Okay. So we need to balance this with respect to charges. So on the first half reaction, I have 2 negative charges here, and on the right side I have 0. So this is the higher, the more positive charge. I'm going to add the electrons over here, and I'm going to add 2 electrons. Bless you. So now I have -2 charge on both sides. In the bottom, I have 4 negatives here and 1 negative there. So if I add 3 electrons to this bottom half reaction, 3 negative charges plus 1 negative charge gives me -4 on the left, and I have -4 on the right. Okay? I need to get the number of electrons the same. So I've got 2 and 3. I'm going to go with 6 again. So I'm going to multiply this one by 3 and this one by 2. I'm going to move that over because 3 electrons. Okay, so I'm going to multiply that by 2. That's going to give me 6 electrons. I multiply 4 by 2, I get 8. And I get 2 here, and 2 here, and 4 there, and 8. Whoops, 8. The top half reaction I'm multiplying by 3. So I'm going to get 6I minus, and 3I2, and 6 electrons. Everybody okay with that? It's like I'm teaching you a card trick, right? It's like, okay, you got to do this, and you got to do this. And you're like, ah. I have 6 electrons on this side and 6 electrons on that side. So I can cross those off. Is there anything else that's showing up on both sides? Water. I've got 8 water molecules on this side and 4 water molecules on that side. What if I subtracted 4 water molecules from both sides? If I subtract 4 H2Os from this side, and I subtract, I don't know where that came from, subtract 4 H2Os over here. Is that going to change the balance of the equation? No. 4 H2Os minus 4 H2Os is 0 H2Os, right? So I got rid of those. And over here, 8 minus 4, now I've got 4. So I've got 4 waters there. You okay with that? I explained it a different way to the Tuesday, Thursday class, and they didn't like it, so we kind of went a different way. So if you don't like this, try the Tuesday, Thursday video. Today's Wednesday, right? Got the same number of electrons, we canceled those out, now we're going to add things together. So I have 6 iodide ions, and I have 2 permanganate ions, and I have 4 water molecules on the left side of the arrow. On the right side of the arrow, I have 3 iodine molecules and 2 manganese 4 oxide ions. 2 MnO2s. And then 8 hydroxide ions. You should verify. Any questions?
If we left the 4, or the 4 on the right,
Yeah, so what if you left the 4?
would our answer be wrong?
So what if you left the plus 4H2O and you left this an 8? Well, is it balanced?
Yes.
Yeah, it's balanced. So if this was one of these show your work problems on an exam, you may or may not lose like 1 point for not having it down to its simplest form. I honestly am not sure what Mastering Chemistry is going to do about that, if it cares or not. So it's best to simplify everything. Any other questions? This is the last one, promise. See, I showed you the last slides coming up. Okay, bounce another one in basic solution. So these are a little more complicated, but you can just kind of ignore the oxygens and the hydrogens and look for the other elements. This one's chlorine and this one's chromium. Chromium. So the chlorine, the thing containing the chlorine has to go to the thing containing the chlorine. And so that's how you decide what goes in each half reaction. So ClO minus aqueous, and over here I've got Cl minus. The other half reaction is going to be the CrOH4 negative aqueous and CrO4 2 minus aqueous. So I'm going to go through this one faster because we're all getting tired of this. Balance with respect to mass. 1 chlorine, 1 chlorine. I got 1 oxygen here. I balance oxygens by adding H2O. So I'm going to add H2O on this side. And then I balance those H's that I added by adding hydrogen ions on the other side. So I've got 2 hydrogen, I need 2 hydrogen ions. First one's balanced with respect to mass. Down here I've got 1 chromium and 1 chromium. Here I have 4 oxygens and 4 oxygens. That's nice, but then there's these 4 hydrogens, so I have to balance those. Balance those by adding H pluses. So I'm going to add 4 H plus on this side. And there I have balanced with respect to mass in acidic solution, but this is basic solution. So wherever there's an H plus, I have to add hydroxide ions. Here I have 2 hydrogen ions, I have to add 2 hydroxide ions. I don't want to mess up the mass balance, I have to do the same thing to both sides. So I'm going to add 2 hydroxides to that side and 2 hydroxides to this side. 2 hydroxides and 2 hydrogens make 2 water molecules. I have a water molecule over there. You can simplify it at this point if you want to, or you don't have to. On this one, let's just leave them and take care of them at the end. Just show a different way of doing it. So here I've got 4 hydrogen ions on the right side, so I need to add 4 hydroxide ions. And then I'm going to add 4 hydroxide ions on this side. 4 hydrogen ions, 4 hydroxide ions, makes 4 water molecules. So I'm going to get rid of those and write 4 H2O liquid. Mass is balanced. Now I need to do charges. First half reaction, on the left I have 1 negative charge. On the right I have 1 negative here and 2 negatives here, so a total of -3. So I have to add 2 electrons to the reactant side. So the charges are the same on each side. You should always be adding electrons to the left on one half reaction and the right on the other half reaction. So if you end up with both of them on the same side, you've got some other issue going on. Start over maybe. 4 negative ones and another -1. So that's a total of -5 on that side. And over here I have -2. So I need to add 3 more electrons over here so that I can get -5 on both sides. Then I need to get the number of electrons equal, again with the 2 and the 3 business. I need to multiply this by 3, the whole equation, so I can get 6 electrons. So let's do that. Multiplying by 3, so that's 6, 6, 3, 3, 3, and 6. The bottom has 3 electrons. I want it to be 6 electrons, so I'm going to multiply by 2 all the way across. So 4 becomes 8, multiplying by 2, multiplying by 2, multiplying by 2, multiplying by 2. So I have 6 electrons there, 6 electrons there, and those cross off. So write down the rest of the stuff. So I've got, for my own reasons, I'm going to put the waters and the hydroxides on the outside. So I've got 6 H2O liquid, so that's this one. And then I've got 8 hydroxide ions. And then I've got 3 ClO minus and 2 of these weirdos. Did I get everybody? Yeah. Then over here, 2 CrO4, that's chromate ion, and 3 chlorides. I ran out of space, so I'm just going to continue below. And here I've got 3 waters and 8 waters. 3 plus 8 is 11 H2Os. And I've got 6 hydroxide ions. So that's balanced with respect to mass and charge, but I've got water and hydroxide ions on both sides. So any questions about that result right there? Right. On the other,
We did
on the previous example, I simplified, or I got rid of the extra water molecules in the half reactions. Here, I'm just adding it all together, and I'm going to take care of it at the end, just to illustrate that you can do it both ways. Personally, I like to take care of them first, because then you don't end up with double terms on both sides. It's shorter, and it fits on the page better. How's that for a reason for doing something? Fits on the page. I have 6 water molecules here and 11 water molecules there. I could subtract 6 from both sides. So I'm going to subtract 6 from both sides. That's going to leave me with 5 over here and none over there. Okay with that? Then let's look at the hydroxides. I have 8 hydroxides here and 6 here. I could subtract 6 from both sides, right? Subtracting 6, this one completely goes away. That's why I wrote them on the end. And subtracting 6, this becomes a 2. Now, if I had started over here, I could get that on one line. Okay, any questions?